Chapter 6. Determinant of a product. The learning objectives of this chapter is to fill some gaps that we left during covering previous topics. The outcomes are learning the determinant of the product of square matrices. We're going to learn what it means to invert a matrix. We learn a formula for inverting a 2 by 2 matrix by hand, and we will see that this is not an operation that we generally want to do by hand. And we're going to learn the matrix transpose. A useful fact in linear algebra is that for two square matrices A and B, the determinant of the product equals the product of their determinants. Now suppose we have A and we have computed the LU factorization. Using the previous fact, we can write the determinant of A to be the determinant of L times the determinant of U. This is very important because now we have a general way to compute the determinant of any square matrix of an arbitrary size. Let's look into an example. Here we have A. We compute the LU factorization. The determinant of A equals the determinant of L, which is the product of its diagonal, because L is a lower triangular matrix, times the determinant of U, which is again the product of its diagonal entries, because U is an upper triangular matrix, and the answer is 40. Let's verify this in Julia. We define our matrix A, we compute the LU factorization and store it in the variable f. And here we see that the determinant of L equals 1. The determinant of U up to machine precision is minus 40. The determinant of the permutation matrix is minus 1. And we already know that the determinant of A must be 40. And again, it's up to machine precision, that is 40. So a remark here is that in general, when we compute the LU factorization in Julia, we have P times A equals LU. Now if we take the determinant from both sides, and using the fact we learned, we write this as determinant of P times the determinant of A equals the determinant of L times the determinant of U. So when a permutation matrix is involved, we need to take that into account. So we learned that the determinant of A in general is 1 over the determinant of P times the determinant of L times the determinant of U. And that is why we see that if we just multiply the determinant of L and U, we get minus 40. Whereas if we consider the determinant of P, we get our correct answer, which is 40. Now a remark here is that a permutation matrix determinant is either plus 1 or -1. So we do not risk the division by 0 here. The answer is always 1 or -1. So up to a sign, we might get different answer if we do not take the permutation matrix determinant into account. All right. Can we generalize this to more than 2 matrices? The answer is yes. We can generalize this to an arbitrary number of square matrices. Suppose we have A times B times C. We can simply consider A times B as a matrix and then write the determinant as the determinant of A times B times the determinant of C, and we can apply our determinant fact to now A times B, and then we successfully separate. The answer is to product of their individual determinants. So this formula extends to any product of n by n matrices. Next time, we will look into the identity matrix and matrix inversion.